Recorded's rolling. It is Monday, September 8th. Welcome back to school. So these projectile puzzles that I gave you guys last week, let's have these due this coming Friday. So I'll work on as many of these with you guys as we can work in class together today. All right, then later this week, I think tomorrow I want to do a Kahoot with you guys. You guys remember we did one for linear motion, right? This conceptual type questions. Right, so I've got one for projectiles and 2D motion. Uh, on Wednesday, I want to take you guys outside. At least I'm looking at Wednesday for this activity. So a ball launcher lab. So I have some ball launchers in this lab closet. I have these little bouncy balls, squishy bouncy balls. So we'll go out to the balcony here later this week. Have you guys fire some bouncy balls straight horizontal. So you're gonna land somewhere on the ground below. Hey guys, just plant this idea today. You guys be thinking about this for a couple days. Can you guys walk up the staircase with the meter stick? Measure how high is this drop right here? How many meters?
Yeah.
And can you have somebody spot the ball and then count how many meters out it is? Right. I also have some trundle wheels. Right. You can either that or meter stick. Right. And then if you know Earth's gravity, G, okay, do you think in principle there's enough information lying around you can calculate the blast speed from this launcher? Right? Be thinking about that. Think about that. We'll be doing that. All right. So be coming up a couple days. Okay. And then quiz this Friday. So this is going to be on kinematic motion. So that's both linear motion and also projectiles. Right. Right. So which is all just these three kinematic formulas right here, and they're hanging up on that poster in the back in the room in the middle from the ceiling. Right, they're right there. I'll just leave them right there. Right. So it's good to know these anyway, but they're hanging from the ceiling. Okay. So I'll cover linear motion, and then projectiles. You just have to be able to juggle two dimensions. Right. Something going on horizontally, something going on vertically. All right, and we're going to solve a bunch of these right now. All right, yeah, you guys ready to go? You go. All right, and then I'll pick up this paper from you guys Friday morning. All right, so the other day, I think we did, I think we did this one and most of this one, right? Is that right? Did this one, most of this one? All right, so what else we got? How about this one on the bottom left? Say a cannon fires a cannonball horizontally at given speed off the edge of a cliff. Right. Oh, by the way, these three on the left side, you guys remember, this picture applies to the three on the left, the three left side scenarios. Right? Cannon on a cliff, fired horizontally. Okay, so you can use that as the picture. Okay? So that's what we got right here. A given height on an alien planet. So I have a cliff height right here. Right. You guys know all the vertical information is in the right half of the table, and all the horizontal information is on the left side. Okay. Because vertical has more stuff going on because gravity is pulling straight down. Okay. Now, we don't know how much gravity because we're on an alien planet. And that's the first question. Number 9. Find the freefall acceleration due to gravity of the planet. It might also be phrased solve for the strength of the gravitational field, something like that. And then, and what's the total speed that the cannonball hits the ground? Now, that was a little more involved, but got to find the gravity field first. So, one thing at a time. So there. Actually, since I've been working from this page, I'm going to get a brand new paper that's different. Let me show this is different. Yeah, this one's different. Just in case you have the same numbers. Okay. All right, so same scenario though. We all have the same scenario. We just have different numbers. So this will be number 9 and 10 from that page. 9 and 10. Okay. Got an alien planet. Got an alien cliff. And let's see, look at my numbers. Why? Oh, actually, you know what? This is if I make this to scale, yeah, let me do this. Okay, this won't be exactly to scale, but be closer, I guess. Something like that. All right, so here's our launcher for number 9 and 10. So I'm gonna blast the ball straight horizontal. I'll call this V sub X, right? What's the block in a horizontal direction, right? Which I did give to you guys. You guys have that number. Okay. And this ball's gonna maybe like land way over here. Like that. Yeah, that's the basic premise, right? Okay. I'll call the height of the cliff H. I'll call the distance it lands from the base X. Yeah, I think that's all we need right here. Right, so I did tell you the blast speed. Now I'm looking at my paper. My paper says, here, can you guys find your blast speed, your launch speed, this horizontal speed right here, horizontal velocity? Okay. Mine says 170. meters per second. Okay? And I have a cliff height. Right? Do you guys find your cliff height? Wouldn't it be this vertical displacement? Isn't that what cliff height is? Right? Vertical displacement. I've labeled y. Mine says 23 meters. So I'll call this 23 meters. Okay. And then I told you where the ball landed, how far downrange. So mine says 276 meters from the base of the cliff. Okay. So here I'll say equals 276 meters. Okay. All right, that's all the given values. And the fact that you know this launcher was straight horizontal. Straight horizontal means v initial in the y direction is 0 meters per second. Okay, so I guess you know that too. Okay? But we don't actually know the gravity field, right? But we can get it from this because there's only one gravity field that will allow exactly these numbers to play out. Okay, everybody gets the fire? It's far? Okay. So we got something vertical going on, the ball's dropping. We also got something horizontal going on. It's going across the field. Okay. Now, what do you want to start with for this particular scenario? Do you feel like starting with, or should we start with horizontal type information or vertical type information? What do you think?
Horizontal.
Yeah, let's go horizontal. Right. Here's why. Right. Because what horizontal information do you know so far? Yeah, you know both these things. You know how far it goes horizontally, and you also know how fast it was going across the field horizontally, which never changes, right? Because gravity only pulls vertical. Right? So if you know those things, can we calculate how much time it takes to get from here to here? Okay. And since there's no acceleration horizontally, there's only one equation you can use horizontally. I'll write down the word horizontal. Horizontally. Yeah, x equals vt. Equals, well, put a little subscript s. X equals v sub x times t. How far across is how fast it's going across times how much time. Yeah. Now, you can solve in terms of variables if you want to. That's perfectly fine. I'll go ahead and plug in numbers for this. So for solving for t, say I know it went 276 meters at 170 meters per second. Say times time. Okay, divide both sides by this v. So that's alpha, right? You guys can divide the 276 over 170. Right? So I'm getting time is 1.6235 seconds on my paper. Now, realistically, that's way too many digits. That's way too much precision. I don't really know this 3.5 is what 3.5, right? But I'm gonna hold on to that because I need to use this and I need to integrate it into another calculation. Right? I need to apply it somewhere else. Right? So I don't want my rounding errors to add up too much. Right? So let's say there should be a 1.62 seconds on my paper though. Let me show us the case. Oh, no, sorry, that was actually a question. Right. So never mind. I don't know that. Right. But I do need to know this. Now let's switch over to vertical. Right. I mean, we had to write a vertical at some point anyway, because guys, gravity field only pulls which way? Down. Yeah, down, which is vertical. Right? So now what? What equation are you guys gonna use to set up this whole thing? Here. Yeah, is that first one? Yeah, definitely the first one. Right? Because this first one has something to do with displacement as a function of time, right? And we just found time. So that's nice. That's useful now. Right? Guys, here's another way to look at this. On this paper, we just found this time using horizontal information. But that's the same time it takes to drop vertically. They're the same time. Isn't that the only variable that does that? Because it's a scalar, not a vector. Okay. So we just found time. So let's make use of that. Okay. And actually, guys, you can modify this or simplify this for this particular scenario. Because when we're talking about displacement, in this case, for this projectile, what displacement are we talking about? How far across or how far down? Yeah, down, because we're talking about vertical. Guys, acceleration for a projectile. Projectiles only accelerate vertically. Right? Gravity only pulls down. This is a vertical displacement. So instead of saying x, I could say y or h. Y or h. Either one's okay. Since on my paper I wrote h for height, I'll just do that. But you guys could write y. It's the same thing. Y or h for like a vertical change, a height drop. Okay. Equals. Right? How about this right here? Because at the point that you launched this ball from the top of the cliff, how fast was the ball moving? Not in general, not horizontally, but vertically. Vertically, it started out initially. Isn't that what this subscript not is? Like initial condition? Initially going how fast up and down? Zero, zero. This ball was going straight to the side. It wasn't moving up or down at all. Now, after some time, of course, gravity takes over and that changes. Right? But initially, it just goes away. So can I just simplify this and this just goes to zero? If I write it out, it'd be like v naught y t, but that just immediately goes away anyway. Okay? Then plus 1/2 g t squared. Right? It's like that. Is that really what this is? Guys, this is strictly a vertical equation. Strictly vertical. When you're working with projectiles, you're either working strictly horizontal or strictly vertical. Right? But time can transfer. Aha, I'm just about to right now. Sure. Actually, what we're staring at right now sort of reminds me a little bit of. You guys remember this reaction time lab you guys did? Right? Right. Which actually started out exactly like that, didn't it? Ah. Right. Unless your friend was throwing the rod, like, come on, catch this. And then they just dropped it. You're right there. All right, so let's see. I know the height. I'm gonna pop that in right here. Right, that's the height. Drop. Okay. I don't know the gravity field. Ooh, but that's what we're solving for. Ooh, I do know the time. I'm gonna save all these extra digits just so that I'm not rounding and rounding and rounding. Okay. It's right there. Right there. Right, you guys see how all this fits together? Now I'm solving for g. So you need to cross multiply the 2. So 2 times the height. I could have done this in terms of variables also, right? But plug the numbers in. That's all right. Divided by the times squared. Right? 2 times the height divided by the times squared. Right? Just a little algebra. Right? So once you got the equation set up, got the numbers plugged in, just a little algebra shuffle. All right. Thank you. All right. That all right? Everybody doing all right? All right. Let's digest that right there. Okay, boom, boom, boom. All right. Hey guys, look at the units here. What is meters divided by seconds squared? Oh, that's meters per second squared, which could just grab a gravity field. Whoa! It's all coming together. 2 times 23 over 1.62 squared. Okay. So I'm getting a gravity field of this many meters per second squared. Okay. That probably shows up as 17.5 on my paper. Let's see if it does. Does my paper have a 17.5 on it? Where did it? Here, it's over here. Let's see, is it? Yeah, that is an option. But bam, it is an option. All good. It's working. How about you guys? Are you guys getting the gravity field on your paper too? Working for you guys? So, exact same process, just a little bit different numbers. I suppose you were on my planet. Would you feel really light, really heavy, or about the same as you do on Earth? What do you? About heavy? Yeah, about twice as heavy, wouldn't you? Because you guys know Earth gravity is about what 9.8 right here, right? And this planet's like 17 something. Woo, about twice as heavy. Yeah. All right. But there's a follow-up question, which is what's the crash speed? What's the crash velocity? So here comes this cannonball. Ooh, does it crash basically on an angle like this? Crash on an angle? Is that true? Right. I'll call it V crash. V crash. And that's the question. What's the total crash speed? Right? Crash velocity? Right? If you point a radar gun at this cannonball, rise about crashing ground. Right? Now this cannonball, in terms of projectile motion, well, it's still going across the field, but now it's also coming down at the same time. In fact, I know how fast it's going across. Dx equals 170 meters per second. That never changed, right? Isn't this 170 meters per second across? That was true all the way across, wasn't it? Okay. But coming down, that would be v final in the y direction, which I don't actually know yet. Okay. But if I did know it, could I just combine it with the horizontal vector Pythagorean theorem and get the total crash speed? Right. So you guys know this is going to end on a Pythagorean theorem, right? Everybody sees that? This is going to end on Pythagorean theorem. Right? But I can't quite get it yet because I don't know v final in the y direction. Okay? Right, you guys ready to find v final in the y direction? Okay. And there's 2 ways to do it. What's one way? Which one of these?
Use the middle.
Middle one? Yeah. All right, let's do the middle one. Right. The middle one, you can get the final velocity in the y direction based on the fall time. Now, if you wanted to use the third one, you could do it based on the cliff height. That would take the place of this x right here. Either way, you'll get the same correct answer. So, okay, so 9 and 10 continues. All right, let's do, middle one. Final velocity in the y direction equals initial velocity in the y direction. It says plus AT. Guys, could that be GT? Same thing, AT, GT. Gravity field is a type of acceleration. And this, what's this right here again? What's initial velocity in the y direction? 0. That's what we did before. Pretty far. So final velocity in the y direction is, okay, take my gravity field. What was the gravity field? Okay, just found that right here. Take your gravity field that you just found. Maybe save an extra digit of precision, meters per second squared. And multiply by the time of fall. Okay, which is something else we had to calculate back here. Time of fall. I'm saving a bunch of extra digits just to be safe. Right there. Okay. So, like, if I rounded too much, if I just call this 17, I just call this like 1.6, well, the answer might not be comfortably close to one of those multiple choice answers. Okay. But I have lots of digits, so it should be safe. Okay, what's that times that? Okay, I'm looking at this many meters per second. This isn't meters per second squared times seconds. Meters per second. Oh, which could describe a velocity. Okay, so that's good. Now we still have one more step to go. So let's look at that Pythagorean theorem triangle. Okay, so I know v sub x, and I just found v sub y. So v sub x was given from the beginning, and for my paper, that was 170 meters per second. So that's always been the case. 170 meters per second across. Okay. And coming down, v final in the y direction. That is my I just found right there. Okay. Right, so the cannonball is kind of going across the field. It's kind of coming down at the same time. So this right here, this resultant, here's the resultant. I'll call V crash. V crash. Okay, that's what we got to find. Okay, guys good? Okay, any questions about? Okay. If you were to watch the trajectory of the ball, okay, it would come in kind of like this until it was flush with the curve right at the point that's crash landing into the ground. Okay, you guys see like a stretched out parabola right here. This would be a parabola, wouldn't it? I'm looking at the path of the ball. Okay, okay. So we got this Pythagorean theorem set up. I'll say v crash equals, would it be the square root of a squared plus b squared? 70 squared plus 2833 squared. Okay, all in parentheses. And this would be meters per second. I was pulled the unit out, meters per second. So v crash. Okay. And I should be getting an answer choice on the paper, or I'm about to find out. What's the square root of that squared plus that squared? Okay. And you know what, guys? Here's a huge hint. I probably shouldn't give you guys. Do you guys see how it's going across the field way faster than it's coming down? Right, like an order of magnitude faster, something like that. Okay. What that means is this triangle is actually a flat, skinny triangle. Guys, if you have a flat, skinny right triangle, is the hypotenuse just a little bit more than the longer leg? Usually is. Yeah. So I'm going to guess this is probably, maybe between 170 and 175. Okay. Great. Let's see. We're going to find out. We're going to find out with you guys. 172. Hey, look at that. Okay. So 172 meters per second. That is the total crash speed. Okay. So is that a choice on the paper? See if it is. Oh yeah, it's right there. It's right there. All good. Okay. How about you guys? Is that working out for you guys?
All right, can you put your paper back up on the screen?
What? This one?
Oh no, the other one.
No. This one right here. Okay, so here, while we're looking at this, here's the roadmap we did. All right, so I told you the height of the cliff. I told you that you aim the cannon straight horizontal, which makes v naught y 0. I told you how fast the cannon blasts horizontally. Okay, and I also told you how far away the ball lands from the base of the cliff. Okay, so what we did is we started with this horizontal information over here. I'll label this horizontal here. I'll label this vertical. Right. We started with this horizontal information, did x equals vt, right? Distance equals v times time. We're able to get the time because there's no acceleration horizontally. Like once it's left the cannon barrel, which is going. Then you take that time, you go plug it in because it's the same time. It takes the same time to go across as it does down. Same time either way. Time is the scalar value. Right. And now you have enough information on the vertical side, you can calculate vertical. Right? So we grabbed this acceleration, which is the gravity field, right? Do some version of y equals 1/2 gt squared, something like that. Got the gravity field. Right? Right. And then we got the crash velocity in the vertical direction, but that wasn't all. Right? We had to take that and combine it with the horizontal component, use Pythagorean theorem, get the total crash speed. Aha. That's good. All right, are we good? We're good. All right. I got one bonus follow-up about this question. Do you guys see this angle right here? This angle? I'll call it theta. Aha, it could be an angle. Right? Who knows? How do you calculate theta?
And inverse B over
Aha, yeah, inverse tan. Here, I got some space over here. So I'll do theta equals inverse tan. Yeah, b over a, so it'll be what? 170 over 28. 170 over 28 meters per second, meters per second. Let's see what is that? Okay. So what's inverse tan? 170 on 28. Okay. Guys, before I hit enter, just eyeballing that. Take a guess. How many degrees from the vertical should that be approximately?
30 something.
Guys, here's 0 degrees from the vertical. Here's 90 degrees from the vertical. It's coming straight horizontal. Is this closer to 0 or closer to 90? And my picture,
to 90.
yeah, closer to 90, right? Okay. My picture's not even to scale. Guys, this is 170 this way. This is only 28 this way. Yeah, I'm gonna guess this is about 80, 85 degrees, something like that. Right, let's see if it is. Oh, 80.5. Okay, yeah, right in there. So that's 80.5 degrees from the vertical. Right? So it's coming in, yeah, 80 degrees from the vertical. All right. You guys ready for the next one? Yeah, okay. Oh, okay. Okay, next one. Let's see. How about this one on the top right? Let's do that one. Right, so cannonball fired at speed 170 meters per second, angle of 30 degrees above the horizontal on a flat plane. Oh, and these three scenarios on the right side, here's a picture that you can use for these three. So we're on a giant flat plane. We got a cannon that's aimed at its own angle from the horizontal and blast its own blast speed, and it's going to land somewhere way out there. Right. Actually, here, look ahead a little bit. See that question number 14 says, how far did the cannonball go horizontally before striking the ground? Right. I think the answer is right here, actually. This thing's right here. There's this whole little derivation problem. Actually, it's not even that long. Okay, to get hold of this and look at it. Okay. It tells you where this equation comes from. Okay. So yeah, let's solve the whole thing, and then we'll go back and we'll check it with this and see if it's the same thing. Right. So 11 through 14. We've got 11 through 14. Right, like that. Okay. Here, I'll get a picture going. Okay, so we've got a big flat plane, got a cannon. It's did I say the angle? Oh yeah, okay. I did give you the angle. Okay, you know if I was gonna have to solve that. Okay, so that's there. There's some blast velocity. Okay, or blast speed. Okay, so I'll call it V blast. I give you this angle here, theta. Okay. And then it's gonna land way over here. Okay, way over here downrange. Okay. Okay, so my numbers go, this is 170 meters per second, and this is 30 degrees. And okay, I did also give you a gravity field. I just put in Earth's gravity field. I probably did that for all the papers. Now, see how I made that negative? You see gravity is negative in this case? Sometimes I do positive, sometimes I do negative. Right? Whenever you throw a ball upwards, in this case, shoot it kind of up-ish, and then gravity's pulling down, isn't that a competing directions? Right. So there has to be a negative somewhere, and which direction is negative is kind of up to you. So I'm calling down negative for this one, saying G equals 9.8 meters per second squared down, which you can express as a negative value. Okay. Right. So what else could you know here? Okay. Whenever you get this scenario, a really good first step to do is to break this blast velocity into components. Say how fast across and how fast up is that cannonball leaving the cannon barrel. You guys get that? Right. Break that into components. This way. Extrapolate this backwards a little bit. Right. So this side, I'm going to label a V sub x. That's how fast is the cannonball going across the field, which never changes. You guys remember that? Like how fast it's going across the field? It's like constant all the way across, right? Because gravity doesn't pull horizontally, and air drag we're ignoring. Right? And so, how do you get this leg right here? Because this is what times what?
30 pounds.
Yeah. So take your full blast speed, 170 meters per second. Okay. And the fact that this leg is adjacent to the reference angle, is that a sine or a cosine? Yeah, cosine of 30 degrees. Alternatively, you could say sine of 60 degrees. It would tell you the same thing. We're going to go with that one. Cosine of 30 degrees. So let's see what that is. 170 cosine 30. Looking at 147.2. I'll throw in another 2 meters per second. Say my rounding for the end, right? Probably a good idea. Okay. Guys, what about the vertical? Would this be 170 meters per second times sine of 30 degrees? I think a lot of you guys probably know this by now. Is what is sine of 30 degrees?
35.
Yeah, 0.5. Yeah, 0.5. So then 170 sine 30 degrees would be exactly 85 meters per second. I don't even need to round on that. That's an exact value, isn't it? Yeah. You can say half of sine of 30 degrees is half, isn't it? Okay, so we got this started. I think what I would recommend at this point is go ahead and fill in some of these boxes. Right? That might make this clear. So under V sub x, I'm going to write 147.22. Under V naught in the y direction, so V initial in the y direction, I'll put 85 meters per second. Now, you guys know vertically, it's a little trickier because gravity is pulling vertically. So it's vertical velocity. Huh?
I'll see the paper.
Oh, this one right here.
Yeah.
Okay. Right. So here. So all I explicitly typed was the gravity field negative 9.8 meters per second squared. Right. Oh, also I meant to mention this too, because if you're going from the ground back to the ground, then what's your vertical displacement for the whole trip? 0. Yeah. Right. Like vertically speaking, right? You started on the ground, you ended on the ground. That's where the 0 comes from. Okay. Right. And then we just split the blast velocity into components. Say here's how fast across the field is going. Here's how fast it was going strictly upward, leaving the cannon barrel. Okay. Okay. Guys, those little puzzle pieces come together. Okay. Okay. Now, you guys also know this is horizontal information here. This is vertical information over here. Okay, so with that in mind, which side, horizontal or vertical, do you have enough information to continue the question?
Vertical.
Yeah, vertical, and only vertical. So horizontal is not really enough to do anything. You could do x equals vt, but run to a dead end. But vertical, aha, I got 3 pieces of information. So I could solve for the time if I wanted to, right? Solve for the hang time, the total hang time, right? All right, let's do that then. By the way, there's lots of different ways to go about solving this. So there's not like one exact correct way, right? But you guys tell me, what do you feel like doing to solve for the time? First, second, or third?
Second.
Second? Okay, I like that you said the second one. Oh, all right. There's let me mention as a thigh.
Doesn't have fun.
That's okay. This is actually an easier one to use, and I'll show you guys why. Okay. Because if you pick the first one, well, actually, the first one's not too bad. Let me do this 2 different ways. I want you guys to really see that whether you pick the first or the second one, it gives you the same answer. Okay. Here, we'll do the first one, then we'll do the second one. So the first one, I'm going to say y equals v naught y t, let's say minus 1/2 gt squared. Can that be a modified version, the first one? Okay. But if you're going from the ground back to the ground, what is the y equal to again?
0.
Yeah, 0. This is 0 meters. Okay. In that case, 0 equals. Okay. Now, in place of v naught y, I'll go ahead and write in my number, which is v naught y. Okay, well, we got 85 meter per second there. We got a t here, and then minus 1/2 9.8 meter per second. I took the negative out already. Right. And then t squared. Right. Basically, we're solving for t. Solving for t. Right. Which almost looks like it's asking for a quadratic equation, except that the fact that it's equal to 0, can I just very simply factor out a t and divide it out and it's gone? Right. So I could pull a t out and then say 85 meter per second minus half of 9.8 is 4.9. There's a t here, and this is all times another t. I could just divide it out. It just goes away. Okay. Then can I add this term over? So 4.9 t equals 85 meters per second squared, meters per second. Okay. And then divide both sides by 4.9. This is all just algebra. Because once you get the equation set, you plug the numbers in, everything else is algebra. Right? So I'm getting the hang time is 17.35 seconds. Okay, get that. Okay. Now, I said I want to do this a few different ways with you guys, so you can really see that there's options how to solve this. Okay, so let's. You guys ready for the second equation? Show you how it's the same thing. Okay. Now you look at the second equation. You guys say, "Oh, let's do the second one." You say, "Oh, wait a minute. I don't know because I don't have via." But you do have via, depending on how you think about this question. Where's the setup? Okay. So I can think of two different ways to set this up with the second equation. Right. So, guys, if this is going up sort of at 85 meters per second initially, and this whole thing is symmetrical and it also lands on the ground where it started, guess how fast it has to be coming strictly down at the crash point?
So
Yeah, 85 down or negative 85. You see it? Right. And you can take advantage of that symmetry, and you can use the second one. Right? So watch this. Let's go v final in the y direction equals v initial in the y direction. I'll say it minus gt. Okay. So this right here becomes negative 85 meters per second. So equals positive 85 meters per second minus 9.8 meters per second squared times t. I can guarantee you I'm going to get the exact same time out of this method that I got the other way. Can I subtract over 85? Is that negative 170 meters per second squared equals negative 9.8 meters per second. Sorry, this is meters per second. Oh. So this is meters per second. This meters per second squared, and I got t. Okay. Divide both sides by negative 9.8. So 170 over 98. Okay. I get in the time of 17.35 seconds. Isn't that exactly what we got before? Okay. So there's 17.35. There's 17.35. I see two totally different methods, but they give you the same time. Okay. Okay. And then here's one more way you can do this that I used to like to do back when I was in high school physics. Okay. Is what if you do this? What if you break this problem in half and you just go to the top point? Would going to the top point, would that be half the total hang time?
Yeah.
And then you could just double it? Okay. Because what do you know about the vertical component of velocity right at the very top? It's 0. You can do that too, right? So watch this. So I could say v final in the y direction equals v initial in the y direction, let's say minus gt. Okay? So this is all going to go to 0 meters per second equals, okay, this is my 85 meters per second minus 9.8 meters per second squared. Okay. Now the catch is this t is not the full hang time. It's just half the hang time. Is that true? So I'm going to say t over 2. Right, and then I'll just double. Oh, okay. Okay, so subtract this off. That's negative 85 meters per second equals negative 4.9 meters per second squared t. Right. Take 85 on 49. T equals. Oh yeah, it's the same thing again. 17.35 seconds. Okay, there you go. I just showed you guys 3 different ways to get the hang time. It's all the same thing. Okay, it's all the same thing. Okay. So I'm showing you guys that there are options. Of course, when you guys get the quizzes Friday, you don't have to do all 3. Just pick one, right? All right, so we got the hang time. Actually, was that one of the questions? Should be.
Yeah.
Actually, yeah, it was question 13. Oh, actually, we've done 11, 12, and 13, didn't we? Because 11 and 12 were find the components of the initial components of velocity. Okay, so I was trying to help you guys out when I made this paper, like trying to ask the questions in order. Okay, so we have 11, 12, and 13. They're all done. You guys good with all those?
What was it? Oh,
12?
like, oh,
What's the initial component? Vertical, initial vertical component? Guys, it's this right here. It's take the total velocity times sine of this angle. So for me, 170 meters per second times sine of 30 degrees came out to 85 meters per second, strictly upward. Okay. Because the point of these questions is like I'm trying to help you break these projectiles down into what's going on strictly horizontally across the field, what's going on strictly vertically as the ball goes up, comes back down. Okay, because those are the 2 dimensions that are acting independently of each other. Right. So like going across is horizontal, going up and down is vertical. Okay, and the connection, the connecting variable would be how much time. It takes the same time to get from one point to another point, however you analyze it, horizontally or vertically. Okay. Okay. But we got one question to go on this one. How far downrange does the cannonball go before it strikes the ground? How far downrange? Okay. And guys, what kind of question is that? Horizontal or vertical? Horizontal. Yeah, horizontal. All right, so look at the picture. Maybe I'll call this distance here x. Here, I got space here. I'll just finish it on this paper. X. Okay. And guys, the equation, anything for horizontal and projectiles, there's only one equation. It goes x equals what? Yeah, x equals vt. Right? Where this v is the strictly horizontal direction. Right? How fast is it going across? V sub x times how much time. Yeah, that's how far it goes. That's it. Right? And we have those, so let's just put them together. So how far it goes downrange equals. So, oh, I got it right here. 147.22 meters per second times. Okay. Now the time, I could show you guys 3 different ways how to get the time. Right. And I got the same number of seconds. So that's right there. Okay. That speed, that time, and how far it goes. You guys okay with that? Very good. Very good. All right, so let's put it together then. That times that. Okay. I'm getting this cannonball lands 2,500 and some meters downrange, about 2.5 kilometers. Powerful cannon. I guess I could write it that way if I wanted to, right? 2.5 something kilometers. Make sure that's an answer choice. We're getting 2,500 and some. Oh yeah, it's right here. Ooh, down to the meter. Nailed it. Bam. All right. Got it right there. Okay. How about you guys? Is that working out on your paper too? Working out? Okay.
what was the answer for that game?
13. How much time did it take for the cannonball? Right. Okay. Here, let me show you guys. So 13, I did 3 different ways. Okay. So one method is you're going to use the first kinematic equation and say if it goes from the ground back to the ground, y is equal to 0. You factor out one of the t's so you don't have to do quadratic, just factors out divided. Right? And you can get, no, I got 17 point something seconds. Okay. A second way you can solve for the time is to use the middle equation and use symmetry. Say, well, however fast it was being blasted up, it's going to come down at the same speed, opposite direction. It is, as long as they're on a level field, you start at the ground, you hit the ground. You take advantage of that and solve for t that way. You get the exact same number of seconds, right? And the third way is you can split the puzzle in half and say, well, if you just go to the top and get that time, you can just double that time. And what's nice about the top point is that there's 0 vertical velocity at the top. Okay? So this goes to 0. But keep in mind this time is actually t over 2, so you have to double it at the end. But you still get the same time. So there you go. That's the answer to that question. All right, guys good? All right. So yeah, we are making pretty good progress because at this point, I think I've covered most of them on here. Right, we did this one and most of this one back on Friday. We just did this one and this one today. Yeah, we got a few minutes left. Great. Right, so with a few minutes left, um, here a couple things. Here, since we were just basically looking at this. Oh, that's what I want to do. I want to check this. I want to see if this works. Right. So let's look at this derivation. We'll test this and see if this works because this will tell you the answer to the one that you guys just answered on your paper. Right. It's sort of pre-solved though. I want to see how this works though. So I got a vertical setup and a horizontal setup. Vertically isn't just okay. I'm going from the ground to the ground. Right. Starts on the ground, ends on the ground. That's 0 meters vertical. Okay. Got V naught sine t, or V naught's the total blast speed. Sine t, the sine of theta, right? Times minus 1/2 gt squared. Right. So I can solve for time in terms of I mean, this is basically what we just did. This is just in terms of variables. Okay. Then I switch over to horizontal to say how far it goes across the field is V cosine theta times the amount of time, where the amount of time has to do with this vertical constraint because gravity's pulling down. So you build a substitution. All right, and then one more detail. Do you guys, does this look familiar from the math class? Okay, show of hands. How many of you guys have ever seen this double angle identity? Sine of 2 theta equals 2 sine theta cosine theta? Who's ever seen that in their lives? Nobody? Nobody? Oh, man. Okay. Maybe they just don't teach that in math anymore. I don't know. Right. But this is nice to know. Sometimes it pops up, like in this one right here. Right, so anyway, how far it goes down range is equal to the blast speed squared divided by the gravity field times sine of the double angle. So let's plug all that in the calculator. I want to show you that this will also answer number 14. So I'm going to take the blast speed. My blast speed was 170 meters per second. I'm going to square that. I'm going to divide by the gravity field, which is 9.8 meters per second squared. Okay. Then multiply by sine of 2 times the angle. Now my angle was 30 degrees, so I'll do 2 times 30 degrees. Right? You guys get that? All I did was I just plugged those starting value. I gave you all these. I gave you the V naught, the G, and the theta. You just plug them in here. I tell you exactly where that ball's going to land. And I know what the answer has to be because I just solved it, like long ways, step by step. I got 2,554 meters. Guys, this better say 2554. Let's see if it says 2554. Bam! Close enough. 2553.89. Oh, yeah. So the ball lands. Landed there. All right. All right, guys, all right. All right. Yeah, we've got a couple minutes, so I'm gonna do this here. On the back side of this page, there's like a hybrid setup. So you have to start out by taking components like v sub x and v sub y. Right. Now where's the ball land? Oh, actually, here I was really helping you guys out on the left side because it's step by step by step. So if you just follow these steps in order, they'll tell you exactly how to solve where the ball lands. Right. So you find the velocity components. You find the amount of time that it takes to get from here to here. Right. That involves a quadratic formula, but I give that to you. I tell you you're going to be using a quadratic right here. Right. And then finally you can say how far does it go horizontally. Right. These other questions are the same premise, just the numbers are a little different. Right, so I'll close down this recording, walk around and answer any individual questions you guys have.